In the last lecture, we presented 3 different versions of the principle of mathematical induction, and at the end, we talked about the well-ordering principle and mentioned that it was equivalent to the principle of mathematical induction. We will prove now that the well-ordering principle is equivalent to the principle of mathematical induction. What do mathematicians mean when they say 2 statements are logically equivalent? To understand this, we first need to know that the majority of the mathematical propositions assert statements that are true if some condition or conditions are satisfied. What that means is that if any of the conditions fail to be true, then the consequence will not be true. Propositions of this type are the atoms that make up the whole body of mathematics. The first part of preconditions, suppositions, or conditions that are assumed to be true are called the hypotheses, and they are usually pre-appended with the if word. Then before the consequence or conclusion, we found the then word. We have already seen examples of mathematical propositions in that form, like if k is a natural number greater than 1, then it can be represented as the product of primes. Many times, the if and then do not explicitly appear, but they are implied. If we can turn tables, reversing the roles of the hypothesis and the conclusion or thesis, that is, if we can make the thesis be the hypothesis and the hypothesis be the thesis, then the hypothesis is mathematically equivalent to the thesis. Discovering that 2 statements are equivalent is something very important. For a mathematician, this is important because it would allow an equivalent translation of a statement, just the same as one is able to translate from English to Spanish or any other language. Even more, the mathematical equivalency of statements has got a meaning similar to equality, like in an equality of 2 numbers. For example, one immediate consequence of equality of numbers we do without even thinking is that we can replace one for the other. Like, one is able to replace 2 everywhere we see 1 plus 1. It is just the same with mathematical logical equivalency. We will study this in more detail at some other lecture. So what this all means is that to prove the principle of mathematical induction is equivalent to the well-ordering principle, we need to prove that the well-ordering principle is a consequence of the principle of mathematical induction, and the other way around, that the principle of mathematical induction is a consequence of the well-ordering principle. Let's refresh our memories about what each of them claim. The principle of weak mathematical induction. If P sub k is some proposition we need to prove where k is natural, we first prove the basis step that P sub 1 is true, and then we prove the inductive step. We assume that P sub k is true for some arbitrary k, and derive from here that P sub k plus 1 is also true. Therefore, P sub k is valid for all k natural. That is the conclusion of the principle of weak mathematical induction. And the well-ordering principle states that for any non-empty subset of natural numbers, there is a minimal integer that belongs to that subset. At first sight, there seems to be no relation between one principle and the other. The principle of mathematical induction says that if some proposition is valid for a first element and also satisfy that if assumed valid for some arbitrary k is valid for k plus 1, then the proposition is valid for all natural numbers. The well-ordering principle also talks about a first element. It claims that any non-empty subset will have a smaller element. First, let us notice that if we can see an element is smaller than any other on a subset, then we are in effect comparing all the elements of the subset in order to find the smallest. The usual way to compare natural numbers is using the relation is less than. We can also see why we need the condition that the subset must not be empty. That is, because if it was, it will not contain any element, and therefore will not have a smaller element. When we pick the subset, this could be finite or infinite. If the subset is finite, we can see it's trivial to find the smallest element of the subset. If the subset is infinite, then it's not very clear how that could happen. Now we can see some relation. On both, we talk about some first element satisfying some property. For the well-ordering principle, that is just the mere existence of that first element in any non-empty subset, and of others possibly an infinitude of elements that belong to some subset, so that an element belong to a subset can be considered as the property analogous to the property P sub k in the principle of mathematical induction. Let us first prove that the principle of weak mathematical induction implies the well-ordering principle. Proof. Suppose P is a non-empty subset of the naturals n, and suppose that P has no smallest element. As you can see, we are actually supposing then that the well-ordering principle is not true. Let us define a subset Q of natural numbers of n such that the elements of Q are not on P. Clearly, 1 is in Q, since if it was on P, then P will have a smallest element. We can also see this is also true for 2. That means 2 is also on Q for the same reason, and so on until we arrive to K, that also had to be on Q, and also K plus 1 had to be on Q, otherwise K plus 1 will be the smallest element of P. But by the induction principle, that means that Q contains all the natural numbers. But since Q contains all the natural numbers, not in P, then P must be empty. But by hypothesis, P cannot be empty. So we arrive to a contradiction. Now, let us prove the other way. That is to show that the well-ordering principle implies the principle of weak mathematical induction. The consequence of the principle of mathematical induction is that P sub k is valid for all natural numbers. So let's assume that Q is the set of natural numbers such that P sub k is false. If Q is empty, then P sub k is true for every natural. So in this case, we are done with the proof. If Q is non-empty, then by the well-ordering principle, there is a natural number k that is in Q, that is the smallest element of Q. But that means that P sub k minus 1 must be true, since if it were false, then k will not be the smallest element of Q. So P sub k is true for 1, 2, up to k minus 1. But then, by the inductive step, P sub k is also true, but that is contradicting that P sub k cannot be true. So, we have proved the principle of mathematical induction is equivalent to the well-ordering principle. If you notice, in the proof we made in the prior lecture about the square root of 2 being irrational, we assumed that it was rational and then tried to arrive to a contradiction. And for that, we use the well-ordering principle. As a consequence of assuming a square root of 2 is rational, we were able to build an infinite decreasing sequence of positive integers, something that is impossible by the well-ordering principle. It is of interest to note that if we regard the subset of all mathematical stamens of certain type that are in existence now, and also the stamens formulated by mathematicians in the future, we can then apply the well-ordering principle to this subset, and assuming as ordering the order of the stamens in the deductive sequence, then we arrive to the conclusion that there is a smaller element to that list, no matter even if that list is infinite. The well-ordering principle guarantees that there is a first element, and not surprisingly, the well-ordering principle itself is chosen as that kind of primal building block of mathematical stamens that mathematicians use. These very special first stamens in the list are called axioms.